name is Sean Rogers. I work in the physics department here at South Seattle College. I teach a bunch of physics classes. Don't have the privilege of teaching this class though. Alice would do a much better job than me on this. But anyway, but this is actually quite nice here. Actually, not all of them, but
yeah, I'll give you some light for now.
yeah, just a little bit of light. That's cool. So really what I want to talk about, which actually dovetails very nicely into a mirrored class, is this idea of how the Earth protects us. All right. You've talked a lot about basically the universe, space, and basically there's a lot of things, a lot of really, really high energy particles in space, right? And we usually call those cosmic rays, right? And the thing about cosmic rays is that they just zip all the way out throughout the universe, but since they have so much energy, they can do a lot of damage, right? Especially when they hit other objects, other buildings, us, right? It's actually how cancer treatments work. They basically shoot very, very high energy charged particles at us, okay? So, what this demo actually helps out here. First off here, anyone knows why, let's say if I bring out a compass, right, and I just leave it alone, what direction does it point?
Magnetic north.
Towards geographic north, right? Okay. And the reason why is because, well, the Earth has this thing what's called a magnetic field, right? So Earth creates this sort of influence that basically makes compasses point towards geographic north, okay? But the thing is that that's not the only source of what we call a magnetic field. It turns out currents can create this stuff too. So if I put a compass near these coils, right, well, there's no current running, that compass is going to point north. But let's say if I go ahead and turn this current on. Someone help me out and take a look at this compass now. Go ahead, yeah. Your name, sir?
Robbie.
Robbie. What direction does that compass point?
West.
Yeah, this way now, right? Okay. The idea here is because now we have another source of the same type of magnetic field that the Earth has here. Okay. So we're going to actually use this as a bit of a model as well. Now go ahead and hit the lights.
Okay.
Thanks. Okay. And everyone might need to come a little bit closer together here because you may need to see this here. So what I'm going to do here, this is basically what's called a fancy electron accelerator here in this nice evacuated tube. Now the thing here is that I need to turn on the boiler here, and you'll see a couple of wires that will start to glow a little bit orange here.
You already made the mistake.
Everyone see these okay?
Recording it vertically.
See a little bit of glowing orange, like right near the bottom here.
Right, yeah.
All right. So what that is, that's basically a giant here that actually, when something heats up to a high enough temperature, just boils off little electrons. Okay. Now the thing is, for those electrons to go somewhere, I need to give them a push. Right. And I do that by activating these electrode plates. That basically pushes these electrons in this direction. Now, in order to do this, I need quite a bit of voltage here. About 200 volts will do. And what do you see? A little bit more voltage on this. What do you see? So right down around here.
A little bit of a green something.
A little bit of green something.
Yeah.
A
Plasma.
little bit of green line here. So what actually is happening here, those are actually the electrons being shot out in this direction. Okay? Now, we know that these are electrons because we can do other experiments that tell us that they are electrons, but this green line really isn't a bunch of electrons. It's actually the electrons basically smacking into the very, very, very low pressure atoms inside this tube and they give off light. And so we gotta say the path that light is the path the electrons take. Now, why do we care about this? Well, notice that we're in the Earth's magnetic field right now, and it's not actually very, very strong. Now, see what happens then when I turn on these coils and turn on the magnetic field from these coils. Anyone? Was this Robbie? Was Robbie here?
Yeah.
What direction did that magnetic field point again?
When we turn on the coil?
Yeah, when you turn on the coils. Yeah, this way, okay? So my magnetic field's gonna point this way, right? What direction do my electrons go? That way? Let's see what happens when I turn this on.
I was going to say, if anybody can't see it,
Well,
oh yeah, you can
Oh,
probably
went
see it
up.
now.
you can definitely see it now. Now what happens? So these are shooting out here, but now what's happening to these path of electrons?
So they're going to
They're going in a circle here, right? It's almost like, you know, there's a big steering wheel on these electrons, right? And what this magnetic field is doing is it's turning it in a particular direction. So instead of shooting it out this way, you get this nice little circular motion, okay? So notice, and the cool thing about magnetic fields is that everything's perpendicular, right? Everything goes at right angles, so that's electrons shoot out this way, magnetic field's this way, and then the push on those electrons are actually up this way, okay? So again, why do we care? Well, let's see what else happens here. Let's say if I turn this bulb so that these electrons actually aren't shooting out this way, but maybe sort of out at an angle. What's going to happen now? I need to really turn the field here to show this. What do I get?
Whoa.
It's like another one.
So so I still have these turning going on here, right? But there's a part, since the electrons are actually going out this way instead of this way, I still have the turning. There's part of the electron's velocity that actually still goes out this way here. So in other words, the electrons start curling around the magnetic field. Magnetic field's this way, electrons go around this way.
Is that what happens with the aurora light and stuff like that?
Okay, now we get to the point here, right? Because, you can grab me that big Earth right there. Because the Earth has a magnetic field, right?
Yeah.
See if I orient this correctly. So we're talking about, say the Earth's about right here, okay? So the Earth is a giant magnet, so its magnetic field is all the way throughout here, right? And again, what do we know about cosmic rays? Well, they're very highly energetic, highly charged particles. And so what's going to happen here is when a highly charged particle, like an electron, like a cosmic ray, gets fired in towards the Earth's magnetic field over here, it's going to cause it not to bump, to hit it, but to actually cycle around the magnetic field lines. And eventually these electrons, or these protons just go in the opposite direction, okay? They're going to eventually get at the Earth's poles. Some travel over here toward the North Pole, around. Some travel over here toward the South Pole. And so what happens, we have a bunch of energetic particles.
Did you give us a brief visual on the shape of the Earth's magnetic field?
Say from about, goes basically, you know, here's the North Pole, here's the South Pole, so basically, actually it's sort of reversed here, actually. So it actually goes away from the north, actually, no, that's incorrect. Away from out here in towards here. So they go basically in big loops right here. Okay, so if I have a particle coming in, it's actually going to just curl around here and hit right here. All right?
Yeah, thanks.
Okay? And so what happens when I have a bunch of highly charged particles right here? Well, charged particles right up here, very close to the Earth's surface here, right where the atmosphere is very thick, you're going to get a lot of collisions like these, and you're going to get a lot of light that comes off. And yeah, you're absolutely right. That's where the auroras come from.
And they're the same color as like green?
Color is going to depend on how much energy these particles give up.
Which is higher energy, reds or blues?
Good question. Blues, yeah. So blues mean more energy escape, and then reds and oranges are going to be less energy given off as well. And so you get the aurora borealis up here. All right, borealis just, you know, Latin for north. Aurora australis down here. Australis is not for south, it just means Australia. Because, I mean, there's quite a few people that live down here. Not really down. I mean, Cape Town and Johannesburg, South Africa isn't too far. Is actually pretty far from the South Pole, and not a lot of people live in Tierra del Fuego. So,
Australia is.
yeah, so Australia it is. Okay, and that's actually where the auroras come from. But this is basically, again, this magnetic field from the Earth is actually our defense against a bunch of high energy particles that come in. What that also means, though, is that when you have, let's say, satellites or spaceships that go up into orbit around the Earth, they get far enough away outside the Earth's magnetic field that they don't have that protection. And so, so part of the designs of the space shuttles or satellites, and I think even the International Space Station has this, they actually have what's called cosmic ray shielding to basically deflect off or to absorb the energy provided by those cosmic rays.
Thank you.
Just power this down here. Yeah, just gotta shut all this down in stages.
Mhm.
Just trying to turn a lot of sources that are off at the same time is not a great proposition. And that should do it. Cool.